Today, I want to present my work at WCV 2021, Ensembling Low Precision Model for Binary Biomedical Image Segmentation. This work is done with my collaborators at Cornell University and Weill Cornell Medical College. The problem we want to solve is binary biomedical image segmentation, especially with sparse labels. Here's an example of internal and external carotid artery in the neck CTA image. One of the challenges of such problem is that background may contain objects that are visually similar to the foreground structures. In this CTA slice, the highlighted bright spot is the foreground internal carotid artery, and the rest of the image belongs to the background class. As you can see, the internal carotid artery is hard to distinguish from external carotid artery. Normally, they have similar intensity, shape, and size. The best clue you can get from the image is the relative position, and even that is not very reliable since every patient is different. A very common method for medical image segmentation is to use a unit that trained on dice or cross-entropy loss. However, this general approach does not give a very good result for our problem because of the ambiguity between internal and external carotid artery. You can see the prediction is confused between the two and output both bright spots as foreground regions. One idea that people use to boost performance is to combine multiple models. Instead of using a single model prediction, you can train several models as diverse as possible and take the weighted average of these models, hoping that this ensemble prediction can better approximate the true posterior distribution. Instead of using regular models for the ensemble, our idea is to train several low precision but high recall models. Between precision and recall, people can build a classifier maximizing one term at the cost of the other. For example, in this picture, the model highlights both internal and external carotid artery, making it a high recall but low precision predictions. We want to make sure that all models always correctly capture the foreground regions, while might make lots of diverse false positive errors. Here, diversity is the key because different false positive predictions can be cancelled during aggregation. We get our low precision models by training with modified version of widely used loss functions, such as cross-entropy and dice loss, by changing the relative importance of false negative and false positive. For the modified loss, higher beta means that it will put more weights on false negative. We train different models in the ensemble with random high beta values between 0.9 and 1. In the paper, we further discuss why this strategy can produce diverse predictions. Here's an example, and A, B, C, and D are the predictions made by 4 different low precision models. Within the red line are the predicted foreground pixels. You can see that they all capture the correct internal carotid artery but make different errors by predicting background as foreground. If we combine them and banalize the probabilistic map with a high cutoff threshold such as 0.9, the resulting segmentation map, which is shown in E, is pretty good in terms of the overlap with the ground truth in F. This is the result showing the dice score for one of the 3 experiments we run to test our method. The ensemble dice score are calculated by taking an average of 5 ensembles. Each ensemble has 10 models. We can see that our low precision ensemble has a high dice score about 10 points compared to the baseline ensemble. We also notice that ensemble trained with a random set of betas performs better than just using the same beta like 0.95 during training for different models. We believe this improvement comes from the model diversity. To test our hypothesis, we capture the pairwise model similarity of the foreground and background regions in the ensemble. Lower value indicates more diversity. A good ensemble should have high diversity in its false positive error but less diversity in the corrected predictions. We can see that the low precision ensemble with random beta has higher diversity in its background prediction and larger agreement in the foreground regions. We also test our method on myocardium segmentation and MS lesion segmentation in MRI and got similar results. You can check them out in our paper. Please come to my session during the conference if you want to learn more about our paper. You can find the code on my GitHub. Thank you very much.